Well, first of all, I'd just like to say congratulations. This is the very last module of the semester. I know we've covered a lot of material, and I hope that in this process you have learned a lot along the way. So today I'm going to show you how to do regression in Excel, and I'm going to break this video up into two parts. The first part will be the setup as well as the assumptions, and the second part will be on the actual analysis for a correlation/regression. If you remember from the online narrated PowerPoints, we conduct a regression when we have two variables that are continuous. So up to this point, we've talked about two variables where one is nominal and the other one is continuous. But now when we have two continuous variables, we cannot use the t or the f test. So we have to use a correlation or a regression. Now remember that regression is just a continuation from correlation, and if you reject the null hypothesis with your correlation, you would naturally proceed to the regression to determine how the variables are predictive of each other. Now, the advantage of regression and correlation is that you get to keep the analysis at the individual level. So remember, with the z, the t, and the f test, we grouped observations, compared means. But when we group those observations together, we remove the individual differences. And we treated everyone within that sample as if they were the same mathematically. Now that limits our external validity, the ability to generalize, in this case, to individuals. If we want to retain that external validity, then we're going to do a correlation or a regression. That way, all our observations are maintained at the individual level, so we can see the impact of what we're measuring at the individual level that allows us to predict for an individual person or an individual thing. So also remember that we're now going to call our variables by different names. So our dependent variable will be our criterion variable. Sometimes this is called the outcome variable. The independent variable will be called the predictor variable. Now, generally they work the same way. We have some variable that we're interested in measuring. That's going to be the dependent or the criterion variable. And that dependent and criterion variable will depend upon some predictor. Now, in correlation, it doesn't matter what you label the predictor or what you label the criterion. However, in regression, you do need to specify which one is the criterion and which one is the predictor. And so just like before, the criterion is the one that you want to measure. The predictor is the one that is used to predict the criterion. And remember, making that distinction in regression is important. Let's go ahead and jump into the data. You'll see that there is a spreadsheet below. There's also a directions page. Go ahead and open up both of those documents. We'll take a look at them as we go through an example together. All right, so now remember that in this first video, we're going to show you how to set up the data. We're also going to talk about the assumptions. So you'll remember from the narrated PowerPoint that our assumptions are quite different going into this last module. We want to make sure we talk about at least 3 of them here. The rest of them you heard in that narrated PowerPoint, so I won't go over it again. So let's take a look at our data here. These data come from a previous semester for the in-class Analytics 2040 course. You see we have 2 variables here. We have absences and we have grades. Now both of these variables are continuous variables. Absences here would be ratio. That is 0 would represent the absence of anyone missing classes. And grades, in this case, would probably be best as an interval variable, because just because you have a 0 for grades doesn't necessarily mean you haven't gained any knowledge or learned anything in a course. It just means you didn't accrue any kind of point credit. And of course, in that very first column, you're going to see the participant ID number. So notice that each ID number represents a student in that course. And so each row represents an individual. And so remember the regression, the correlation retains the individual differences. We're going to retain these values. We're not going to group them together and try to treat them as if they're the same. We're not going to group by low absences and high absences. We're going to retain the actual values. And that's actually going to increase our variability, but in a good way, so that we retain the fact that people differ from each other. And what I mean by in a good way is that we're able to increase the external validity to be able to generalize our findings to individuals, as opposed to grouping it together and increasing our internal validity at the expense of the external validity. And again, refer back to that narrated PowerPoint when it comes to internal and external validity. So let's take a look at the code book. So as mentioned before, absences is the number of absences in a semester. Grades is the student's grade currently in the course. So it looks like we have a scenario here. So let's take a look at it really quick, make sure we're all on the same page. And so research consistently demonstrates a significant and large negative correlation between absences and grades in college coursework. So it looks like here, if we have a negative relationship, what we're saying is that as absences increase, grades tend to decrease. Another way to look at it is if grades are increasing, that usually means absences are less or are decreasing. So let's suppose we want to know if absences predict a student's course grade. We decide to measure the number of days missed in the course grade for each student in an introductory statistics course here at Auburn University. So we want to know, do absences seem to matter in statistics courses? So let's use an alpha 0.5 to answer this particular question. You're going to notice here that the R distribution looks a lot like the T distribution, which means that we can have one and two-tailed tests when it comes to correlation. In this particular scenario, we see that we have previous research, and that research indicates a negative correlation between absences and grades. That means we have a one-tailed test here. So we would expect that our correlation to be a negative value once we do our calculation. Because of that expectation, we can do a one-tailed test where our critical region is going to be in the negative side or the left side of that distribution. Now let's go back to the data page just really quick here. I do want to point this out. Notice that each row represents a person. And so this person here had 10 absences during the semester and a course grade of a 74.65. Whereas this particular student or participant had 4 absences with a grade of 89.14. So it's important that we keep these observations in the same rows. So whenever we sort, or if we sort these data, we want to make sure that we expand the selection to ensure that each of these values stays with its corresponding participant. Okay, so that's the introduction to the data here. Let's go ahead and take a look at our directions and let's jump into this analysis. So you'll see we have several steps here. The very first one is to set up your data, prepare your data set. We want to make sure that we have 2 values for every observation. So again, for every row, there should be 2 values, one for absences and one for grades. We can scroll through and see if there are any blank cells, and I don't see any here. This isn't a fairly large data set, but if it was a large data set, we could sort each of the columns and then look for blank cells at the bottom. If we had any, we would delete those observations because again, for us to do the analysis, every participant, every observation needs to have 2 values, one in each one of the variables. It doesn't look like we have any missing data here, so I'm just going to continue to the very next step. So step 2, we're going to create a scatter plot of the variables. So you remember in that narrated PowerPoint that we had to look at a scatter plot to determine the last 2 assumptions. So we'll need to get that scatter plot first before we move too far into the analysis. So to get that scatter plot, we're going to highlight the columns that we want to create the scatter plot with. We'll click on our Insert tab, and then we're going to select the icon for scatter plot under Charts. And we're going to select that very first option. So let's do that. I'm going to highlight our 2 columns for absences and grades. Now it's important to note that you want to make sure that your criterion or your dependent variable is in the second column. So that means you need to identify which variable is the predictor and which one is the criterion. So in this case, we want to predict grades. Grades is what we're interested in measuring. We want to know, do absences affect grades? So if that's the case, grades are my criterion, absences is my predictor. So can we predict someone's grade in the course based on the number of absences that they have? So once you have those 2 columns highlighted, go ahead and go up to Insert. You're going to see under Charts, there's several different options. We're going to click on the Scatter Plot option. So it says Insert Scatter. We want the very first option. So that's going to be this one right here. And notice that it gives you a preview as well. And so there's our first scatter plot for grades and absences. Now you're going to notice here that there's a whole lot of what we call chart junk. So things like lines in the background that we're going to want to get rid of. We don't have any labels on our axes. So we want to make sure that we put in labels as well to make our graph a little bit more clear. So let's go to our directions. So to make our graph look a little bit better here, it looks like we're going to click on our layout for labels and title. We're going to select the very first option. We're going to remove the background lines in the legend, and then in process, that's going to give us labels. And we want to go ahead and enter in the title and labels for our particular graph. So I'm going to go back to my Excel spreadsheet here. I'm just going to click on my graph. And you'll see in the left-hand corner, quick layout. We're going to take that very first option. You're going to note that's going to give us labels for each of our axes. I'm going to click that one. That gives us everything that we need, a title, labels. And now we want to remove all that chart junk. We don't need the lines in the background. So if I click on one of those lines. Notice that they all highlight, and I'm just going to hit delete on my keyboard, and it's going to get rid of those lines in the background. I also don't need this legend here, so I'm going to left click on that legend, and I'm going to hit delete, and we're going to get rid of that legend as well. And so now my chart's looking a lot better. I'm now going to go down to my x-axis. I'm going to change it. I'm going to put in my label here. So these are absences. So I'll label it as absences. And then on my y-axis, I have grade. Put course grade in there if you'd like as well, but there is the grade for the course. And so overall, just looking at this scatter plot, you do see a trend that it looks like it's a negative trend. So as absences are increasing, it looks like grades are decreasing at a steady rate. We do need a title for our graph, so let's go ahead and do that. This title is just like it was at the beginning of the semester. So remember, we want to include both our x and y axis, and we want to include the population that we're interested in measuring. In this case, it looks like we're interested in all college students in general based on our scenario. So we can say college student grades predicted by number of absences. And that's it. That is our scatter plot. And now we can take a look at it, and that's going to help with a couple of our assumptions. Now, the two assumptions we're particularly interested in here are the last two. So remember, one of those assumptions is that our variables should be linearly related. So in other words, that when I'm looking at this scatter plot, the relationship should be best represented by a straight line. And it looks like that's the case here. Realize the line is not going to go through every single point. It doesn't have to. Just in general, is that line a straight line when I'm looking at the trend in the data? And it looks like it is. Now, if it was a non-linear trend, then maybe as absences increase, it may be fairly flat, but then as you get to higher absences, you see a steep decline. That would be a non-linear trend. Another non-linear trend might be, for some reason, if we had, as absences increase, grades increase to a point, but then over time, as absences continue to decrease, then grades started to decrease as well. Now, I wouldn't expect that trend in this particular type of scenario, but that would also be a nonlinear trend as well. And so notice that in all these cases here, that the line of best fit won't be a straight line, but will be some sort of curved line. I can think of one more trend is maybe a cubic trend that as absences increase, there's not much effect on the grades, but then it might decrease sharply where there's mid absences, and then it might level out because maybe you just missed too many classes and your grade's just not going to be impacted either way once you get over like 15 or 20 absences. And so all those would be non-linear trends. In this particular case, it looks like, based on the data that we have, that we can best represent this data set with a linear or a straight line. If I was to write out that explanation, which I'll ask you to do on assignments and exams, we might say that yes, it appears that a straight line function best represents the relationship. In this case, as absences increase, grades decline at a steady pace. And that would be a good explanation of what you see in the particular scatter plot. Now, in this case, it's pretty clear. It's not always clear when it comes to determining a linear relationship. Usually when you have smaller number of observations, it becomes harder to determine linear from nonlinear trends. In those types of cases where it's ambiguous, what I'm really looking for is your explanation, not whether you are correct in your interpretation. So I'm more interested in, can you explain what you see, and do you know the concept of linear relationship as being an assumption? Now, the other assumption of concern is homoscedasticity. Now, again, you don't need to be able to say that word or even be able to spell it. You can just say equal variances, and that's perfectly fine as well. So we have this assumption of equal variance in the population. What we're saying there is that at any level of our predictor, at any value of our predictor, the differences or the spread in our criterion should be the same. Now, when we're looking at our scatter plot for this particular assumption, we are looking at it in general, not for every single observation. So for the most part, do we have equal variances? And so looking at this particular scatter plot, I see I do have an outlier here that may affect how I determine whether I have equal variances. Again, it's in general, not for any particular point. It is okay to have some points that stray from the rest of your data and still be able to say that you have equal variances. But for the most part here, just looking at the graph, it looks like we have equal variances, because as I go from left to right on my x-axis, the spread of the observations is roughly the same all the way down the regression line. And it doesn't look like it deviates much along that path. So it looks like we have pretty good equal variance here. This is actually really good for using real data. Often it's a little bit harder to interpret. So some examples of when you don't have equal variance. So maybe at low levels of absences, the spread in the values are fairly equal, but as you increase on absences, you increase variability. So maybe there's some people still doing well in the class, but there's also more people who are not doing well in the class, in which case you start to see this funneling. And that would be a good example of unequal variance. Sometimes in graphs, you'll see a trend where it's wider at the front and then it gets narrower and then it widens out. Again, that would violate our equal variance assumption as well, as would wide variation that then narrows down as you go from left to right on your graph. Essentially, we want equal variance because one of the calculations we do is for the standard error of the estimate. That standard error of the estimate gives us a measure of how much error is in our results. And in our mathematical formula, we apply that error equally across all levels of the regression line. And so if we have unequal variance, at some points on the line, that standard error will be valid, but then at other points, it won't be valid. And so we want equal variances, so when we apply that standard error, that encompasses the entire regression line, not just part of it. So now we have our scatter plot here. I'm just going to move it over to the side. We need to get some descriptive statistics. So remember that another one of our assumptions is that we need to assume that in the populations that those distributions are normally distributed. But remember, we can't use the central limit theorem here because the central limit theorem only applies to group data. It does not apply to individual data. You remember, regression and correlation are at the individual level. So that means we got to go back to module 2 and we have to calculate our skewness statistics and compare it to our table. All right, so I'm going to go back to our directions document. And you see in step 3, we need to get our descriptive statistics. We know how to do that. And then we want to check for normality of each of our variables. And again, we'll go back to this skewness table and we'll use it to determine whether we can assume normality or whether we can conclude that maybe we have skewed data. So going back to our Excel page here, let's go to data. We'll go to data analysis, get our descriptive statistics for each of our variables. Those are one for absences. Let's get grades. Okay, so there's our two variables. Now what we're interested in here, again, is the skewness statistic. Now, of course, we are interested in the means and standard deviations. We'll report that in our analysis as well. But for the assumption, we're interested in this skewness value. So you're going to notice here for absences, we have a value of 1.21. Now, I don't need to look at my table to know that that's skewed, but we'll still look at the table. And then we also have for grades a skewness of negative, it looks like roughly 1 if we're rounding to 2 decimal places. Of course, we will need to know our count as well. So it looks like we have a count of 78. So let's look at our directions page. We're going to look at the skewness table. We have 78 observations, which means we're going to be looking at this row right here. So we don't have 78 exactly, but we're just going to go to the one that's closest to. And it looks like 80 is the closest value when it comes to our number of observations. Now it looks like for us to determine that our distribution is normal, we need values between plus and minus 0.41. And because our number of observations are the same for both of our variables, that criterion is going to apply for both of our skewness statistics. So looking at this first one, 1.21, it does not fall between plus or minus 0.41, and it's a positive value. So it looks like in this case that absences is positively skewed. So in other words, we have some outliers where most students have fewer absences, but there's a few students with many absences. And then if we look at the skewness statistics for grades, we see that -1 also falls outside of our criterion of plus or minus 0.41. Because this value is a negative value, it looks like we have a negative skewed distribution. In other words, most students perform well in the class and get higher grades, but there's some students who don't perform well, and that's skewing the distribution in that negative direction. So what we typically do at this point is we would transform these variables until we can assume that they're normal before continuing to our regression and our correlation. To keep this module manageable, because there's a lot of new material here, I'm not going to add that level of complexity here. We're just going to answer our assumption, in this case, say, no, it does not appear that our distributions are normal, and we would report both the skewness statistic as well as the cutoff. So just like before in Module 2, we reported the skewness statistic and the cutoffs, but now we're going to do it for 2 variables, not for 1. Just make sure that you're doing that when it comes to that particular assumption. But at least in this example, it appears that we're not meeting the assumption of normality. We have skewed data. That means when it comes to our conclusions, we may be less confident in the results. That doesn't mean that the results are not valid. It just means we have less confidence in them. And we would want to rerun the analysis once we transform those data. Like I said, I'm not going to ask you to do transforms in this particular module, but in practice, you would want to do that before actually running the correlation and the regression. So that's going to conclude this very first video. So again, we covered how to get scatter plots, how to read those scatter plots to answer the last 2 assumptions when it comes to correlation and regression. Then also getting our descriptive statistics to check the normality of our variables. In the next video, I'm going to show you how to do the actual regression analysis and how to interpret the output. So I'll see you in a bit.